Hello, my name is Alfie Keary and I am your presenter for the Emoco module on Industry 4.0, 5.0, Robotic Tele-Operation for the future of the Internet of Skills. First, I would like to introduce our partners involved in the project. I work for an organization called Tyndall, the Tyndall National Institute. Secondly, our partner Analog Devices, involved in the European project, the Emoco project with us. And thirdly, Mdalo Technologies. Web links for all of the three partners are on this slide. So you're very welcome, and we're going to be looking at robotic teleoperation and its benefits and requirements in order to deliver what module. We will present it in a number of parts. Firstly, we'll give a general introduction in this section. Secondly, we will actually dive into a little bit more detail on the Internet of Skills and refer to the Emoco project and specifically the use case 3, which the partners are involved in, the three partners, Tyndall, Mdalo and Analog Devices. We're going to give you, in part 3, we actually had a presentation in Eindhoven where we presented various video demonstrators of the project. So in part 3, we will present a number of these videos, but in the overall context of robotic teleoperation and the Internet of Skills. And finally, we'll have a wrap up and we'll look at some of the features and challenges in relation to the Internet of Skills. We will give you some definitions, particularly the term Industry 4.0. It's no longer the future. That is exactly where we are today. So really on a global scale, you're looking at manufacturing and industries coping with various aspects and integration of intelligent digital technologies, and all this applied in the context of manufacturing and industry processes. Things you'll hear about, of course, you may be well aware of Internet of Things, but this is Internet of Things specifically in a pure manufacturing and industrial context. Extremely relevant today is the AI implications and machine learning, how the cloud is actually utilized, the whole concept of big data processing, and ever increasing complexities of automation and robotics. So that's kind of where it is today. And over the next few years, that is certainly going to mature in all continents across the globe in terms of the future of manufacturing in various industrial sectors. So take it a few years ahead from now, and it's already emerging. We start talking about Industry 5.0, and that will be a build on what I've already talked about, Industry 4.0. And that's where, I suppose, the robots, I like to refer to it as the robots coming out of the cages. So the robots are starting to emerge out of controlled environments, and these smart machines and robots will be ever increasingly interacting with humans in not only manufacturing, but all forms of societal activities. You'll hear terms like swarm robotics, collaborative robotics, collective robotics, and I've no doubt there'll be some other terms they'll actually introduce over the coming years in relation to Industry 5.0. So this is a good reference. It comes from a paper by Dohler from Ericsson.com. And they specifically define the Internet of Skills. And what we're looking at here is clearly remote robotics is a large part of it, but it defines the Internet of Skills as an infrastructure that enables the delivery of physical experiences remotely. So that is the essence. And a definition I would very much relate with. It's set to revolutionize operations and servicing capabilities for industry. So there will be a massive transformation in terms of how things are sorted, how things are fixed, how skills are transferred, how problems are solved. And particularly, this paper talks about the integration and capitalization of various fields of science and engineering. So Internet of Skills will demand electrical engineering in terms of communications and networking, all of the aspects of computer science and new fields of some computer science to be developed will certainly feed into the Internet of Skills, and particularly the advances in robotics. And that's where we are, through the Emoco project and our use case 3, very interested in where robotics are going to go as they emerge out of, as I say again, the cages or the constrained infrastructure of traditional industry to basically work with us, walk around with us, and indeed interact in a social way with humans in a manufacturing industrial context. So that's, there's some graphics there that show you the complexities of what's involved when we look at the potential to communicate across the globe in the Internet of Skills concept. So you've got various devices at the user ends here. You've all forms of routers and servers, gateways, networks, complexities of all forms of different protocols, and then interactions with different devices. And in a lot of cases, this will be intelligent machines or intelligent robotic systems. So that's a good reference if you want to refer to that and go into more detail in relation to the internet. Here is another reference that we've used, the future of smart manufacturing. I'll go through this fairly quickly because I've possibly mentioned a lot of the points, but it talks about the touch and feel of the internet. So, you know, that basically robots will become, I suppose, they will move from the traditional, very heavy industrial look and feel into systems that can work closer with us and won't hurt humans if we actually start to interact and collaborate with them. So they'll have sensing capabilities and they'll be able to touch and feel things, and we'll be able to get haptic feedback from a robot if it's doing a particular task for us. So they are some of the things. They talk about things like the tactile robot and the tactile internet. As already discussed, this is where they see remote telerobotics playing a major role in the advancement of the Internet of Skills. One of the very important things, as the robots come out of the labs and come out of the cages, you're going to have to see a major increased focus on the safety for all forms of interaction with these future robotic systems. That again is a very good reference. I like the graphic because you can see it's going up here on the y-axis, the increased levels of human interaction intensity, where we're moving up to eventually fully connected and collective interactions with robotic systems and machines in the future. And you can see here where we started off with the very, very basic robotic arms. Then they've started to move up a scale, and particularly in the last 12 to 18 months, we're seeing a number of major players focus on the mobility of robots. So not only are the arms in terms of movement of robots, which have been addressed for decades, I would say now, but the ability for robots to stand, their movement capabilities, and to be able to move around fairly complex environments are becoming an increasing target, particularly for the advanced robotic manufacturers. So, and that then is, I think I've already mentioned the reference to swarm robotics and collective robotics, where you're seeing that you could have a group of robots working on a collaborative task together, and perhaps in conjunction with humans as well. So you're really moving, it'll take quite a number of years to move in this direction, but that is no longer a futuristic possibility. It is actually all the elements, the science, the engineering, the computer science, the telecommunications, all those factors, the psychology, all of those factors are starting to move the whole concept of Industry 5.0 in this direction of robotic collectives, and particularly with reference to the Internet of Skills. In the next section, this is specifically our particular project. You can see that we've got an operator end, and this is where there could be typically be a user. You have all of this complex communication infrastructure. If you're going across a typical manufacturing campus, the amount of data that's communicated. So you're dealing with generally what's called industrial internet protocols. And then there's interactions at the other end with the robot side of it. So we can refer to this as the operator end or the robot end, or we like to call this the local end and the remote end. And there could be a distance of a few kilometers, or indeed we could be into the thousands of kilometers between the local and remote ends when we're talking about a robotic teleoperations platform. Finish off this section, we would like to bring it back to, I suppose, a more realistic set of issues that surround Internet of Skills and robotic teleoperation. And a lot of talk today is about edge computing. So I think before we finish up this brief introduction to you, we would like to talk briefly about edge computing. Without going into a detailed definition, it's really putting the computing power within the location of a manufacturing facility, exactly where that computing power is needed. So generally, these type of edge devices, they're like typical printed circuit boards, but they have enormous processing capability, like a graphical processing unit. And there's quite a number of players now, all producing these dedicated edge computing components. So why are we looking at the edge? Well, one of the biggest problems in robotic teleoperation, and it will be for the foreseeable future, is the concept of latency. And edge computing is addressing this problem of latency. It's not going to eradicate it, but it would aim to minimize latency when you're building the types of robotic teleoperation systems that we're going to require in the future. Edge computing also provides what's called a scalable architecture, because that architecture can be distributed across a factory with defined functionality, and you can scale that into a whole suite of integrated services within a manufacturing/industrial context. The edge enables to minimize data. So if we can keep the computing local, then that's going to minimize the actual traffic and the communication requirements if you're interacting with central cloud capabilities. So this again is a major plus, and why everyone is excited about the advancements of edge computing in the future. The robustness here is that they can provide redundancy. They're expensive, but not extremely expensive for manufacturing organizations. So you can provide backup and fault tolerance. So if something happens, one of those connected edge components, you could have a backup device monitoring, and once there is a failure, then that backup device is available and is able to intelligently kick in and ensure that a operation does not fail in a manufacturing/teleoperations context. Another aspect is that the local decision making is that you're not relying on the cloud and the connectivity. And again, the bandwidth issue here is a problem. If you can make the decisions locally, then you're not going to be dependent on external connectivity to a cloud-based. The other side of edge computing, and increasingly today, is that the intelligence is being built into the edge devices. So what we're seeing is that there's an ever increasing amount of edge components with dedicated AI hardware architecture and software architecture. So the action going on here is to reduce the complexities of the inferencing on the AI systems that are being built into edge components for various manufacturing and industrial activities. The other justification is the privacy and compliance. Again, if you don't have that external interaction with the cloud, then various industries are under very, very strict compliance and legislation criteria. So this actually constrains any external data flows or data transfers with cloud providers, i.e. third-party organizations. So the edge is addressing this aspect clearly. Customization is obvious because you can actually use these edge components to develop your own very specific application for your organization. So it allows for customization of teleoperation solutions, but also a lot of other aspects of your manufacturing process. The cost efficiency is clearly one of the major factors. I've addressed most of this in terms of reducing your cloud infrastructure costs and your telecommunication costs and your data transfer costs. And finally, real-world deployment. The teleoperation in remote or challenging environments. So the fact you're not dependent on external services, i.e. cloud and data services, AI processing capabilities, you have the potential to build, for example, remote teleoperations into mining activity. And that's actually one of the major use cases of the Imoco project, is the potential to develop mining equipment and robotics that could be managed and manipulated remotely. So this would all in the future be enabled by the potential of advanced edge computing with AI and machine learning powered systems. A brief introduction to Industry 4.0, we talked about a little bit about robotic teleoperation, which we'll go into in more detail in part 2. We talked about edge computing specifically, and all of that is being framed in the context of the Internet of Systems. So thank you very much for listening to me for part 1 of our education module, and I hope you'll join me in part 2, where we dig down into a little bit more detail. We introduce you to the Imoco project again, and we talk specifically about our use case in robotic teleoperations with reference to the Imoco project. Thank you for listening, and I'll talk to you soon.